I'm Gian Merlino. I'm from Imply, a company built around Druid. I'll be talking later, but not right now. I'm also a committer on Druid and part of the Druid PMC, the group that directs the Druid project. I think we got a few other PMCers and committers here, so if you've been doing any mingling, you might have met them, and if not, you can meet them after the talks. And without further ado, I'd like to hand the mic over to our host here at MZ.
So I'm Josh Lelowitz. I head up the data platform here, and also want to extend my welcome to MZ. We're super excited to be hosting you and show you some of the great stuff we've been working on. And I'm staying away. And we're also always hiring, so here's some information to jot down. Thank you.
Thanks, Josh. Hey guys, so my name is Pushkar, and I lead the core engineering team here inside Data Platform. And so this will be our schema of presentation for today from MZ. I'll be walking you through the high-level introduction of what we use Druid for. I'll also be giving a glimpse of what does our infrastructure look like. For last 1.5 years of our journey with Druid, some of the problems that we have faced, we'll be talking about that. Along the journey, we'll be joining my colleague, Igor, who will be talking about the game analytics use case at MZ that we use Druid for. And then I'll have my colleague, Vikrant, talk about the marketing analytic use case. So let's get started. So here at MZ, every day we are making hundreds of decisions. All of them involves data. Some of these decisions are made by human, some of them being made by machines. What you see here on the screen is one of such decisions, right? You see two creatives. For people who are not familiar with ad tech, creative is something that you see in an ad. It could be a video or an image. So you see these two creatives both have very similar composition here. Both have Arnold in them. So the point of this slide is that we are making decision like which among these two creatives is doing better than other when the ad is being shown to the user, right? So there are different attributes like click and conversions, and it depicts like we have similar decisions that we are making all throughout the day. So 1.5 years back when we started our journey, so you would have guessed by now, all of these decisions involves looking at the data in real time, as well as looking at the data in historical. We did not want a system which is fragmented for our business user. So when they have to go and look at the data in real time, they'll be using one platform or tool, versus when they are analyzing historical data, they will be going to another tool or platform, because that increases basically their reservation against asking questions related to data. And whenever our experience is that whenever it's difficult for the user, they typically don't ask those questions, right? So these are the fundamental decisions that are nowadays at MZ powered by Druid. So on a high level, this is how our architecture or infrastructure look like. We use distribution of Hadoop from Hortonworks. On top of that, we have Druid, and we use a distribution from Imply. On top of these two things, we have two categories of applications. First categories of applications are the one which is allowing us to ingest data into Druid, and second category of applications are which are allowing our users, both human and machine, to explore data that is getting stored in Druid. So the first category belongs to like we use Kafka. I mean, after all our real-time ETLs are done, we publish the message to Kafka. From Kafka, using Tranquility, the data makes its way into Druid. We also use Spark for all the batch ETL that we do on data before it goes inside the Druid. On the right-hand side, you see two applications, the Superset and MZ own app. Superset is again the front-end facing tool, which allows human user to do the exploration on this platform. We also run variety of application on top of this infrastructure, ranging from our normal applications looking at behavior of data in real time and historical, to some of the much more involved applications like our data science application, which is doing fundamental predictions about how the overall economy of the game is folding in real time. I wanted to give, am I audible without the mic? Oh. So I wanted to give a glimpse of what does data looks like at MZ. And this snapshot we captured 3 months back almost, when we were doing a preparation for a similar presentation. So we have 40 billion messages per day that is being processed by our Kafka cluster. We have close to 250 plus topics, and the partition ranges around 4K. Not all of these topics have a similar setting for the partitions. We run 3 Hadoop clusters in production and multiple ones in different other environments like for staging or dev work. The largest Hadoop cluster at that point of time comprised of 300 nodes. We had 5 petabytes of unreplicated data in Hadoop ecosystem that we were storing. It includes all of these data that we are processing. So now the natural question here is that where is this data coming in from, right? So we have on a very high level 2 category of application that is ingesting this data. We have our own game, which is generating huge volume of data in real time. And then we have our marketing platform. So just to give you an example or a feel of scale that our marketing platform deals with, we publish ads on like 100,000, close to 100,000 apps, which have users in nearly 200 countries. We serve nearly 750 million impressions a day across these ads. The data comes in from, and this is mostly the second category of data that comes in from 300 distinct sources. That includes data coming in from our partners, that includes data coming in from other third party that we integrate with, for example, attribution site providers. So how does Druid stand in front of this data? So right now, Druid has like 3 clusters running in production. We have 30 plus data sources combined all 3 clusters, and we are holding 50 terabytes of data. Now, one more pattern that emerges here, that we have a lot of data when it comes to Hadoop, but we have comparatively smaller data set when it comes to Druid. I think this is one of the beauty of Druid, that the compression runs so fine that we don't need to like worry too much. I mean, the data, when it makes its way to Druid, because of the nature in which it is arranged and the beautiful compression that Druid does, it gets highly compressed. And right now we are having like close to 50 terabytes of data. So about the challenges we faced, I think when we started, the first problem I remember even today that we faced was, since we were running a distribution of Hadoop, which is not as pristine as the open source one, so we had dependencies issues. We used shadowing on top of Druid because that time that was our knowledge about managing the configuration and how to use the class path first. In later version, we started to use the distribution that comes from imply, and we use class path first to basically deal with all the dependency issues. When we switched to point 9 of Druid, we pretty soon got into this Jetty bug, the Jetty on the Jetty containers that all the Druid services runs in. And the typical symptom was that under high load, under spike of queries, the threads would get blocked, and at some point of time, cluster would just become non-usable. We got the Jetty patch thanks to the imply team, and after that, it worked pretty well. So, as I talked about earlier, we use Tranquility for all our real-time ingestion. Reason why we have not moved yet to Kafka indexing service is because our Kafka versions are still old. It's not up to what Kafka indexing service needs. We face some of the problems with Tranquility for the real-time ingestion. One of the prominent one being during restart, like whenever the index spec is changing, we need to restart Tranquility, and that causes sometimes duplicates. And given that a very strict SLA that we have to maintain on HA and the correctness of the data, we somehow find that pretty interesting. When we started with pretty close to what come out of the box setting for most of the processes. And then we started, as our load increased, load of ingestion increased, basically load on queries increased, we started to see some JVM issues. And not all the time JVM problems are in JVM parameters. We started to then also look around what was causing those memory issues. And during the same time, we moved to point 9, which provides the V2 of query, V2 engine for the query. And that, along with some of the JVM fixes that we did, helped us a lot, because we run a lot of group by queries, and switching to the V2 version of group by query engine helped us a lot. Also, pretty recently, almost 3-4 months back, we started to run into caching issues. Caching issues for us, what does it mean? That we were using Memcache as our initial cache technology, and at very high pressure, basically the Memcache network communication itself would become a kind of blocker, right? We deployed a few months back a dual cache policy where the first level of cache is local and followed by a Memcache behind it. That helps a lot. This problem still comes some time, but it has drastically reduced from where it originally existed. Right now, we run like our one of the live cluster does not have priority implemented on it. So all of the queries get the same weightage when they are running, right? So we have varieties of queries, some running our real-time dashboards, some where users or machines are exploring data. And this causes problem when, like, for example, a long-running queries hogs the resources, and the dashboards, all of a sudden they stop basically getting refreshed, meaning the real-time queries are getting blocked. One of the way we have dealt with it so far is that, again, this is also because of a very strict SLA on our HA. And when I say that strict SLA on HA, I'm talking about minutes. We can't have our primary cluster go down beyond a few minutes, interrupts business. So we deployed a technique where our primary cluster contains years of data, and basically people are exploring about it, while our secondary or backup cluster contains just few months of data. So in worst case, when the primary has performance issue, we switch user to our backup, and that basically unblocks, because they can only query certain amount of data. that blocks while we investigate issue along with the employee team what's going on in the primary. So I already talked about what does the SLA, strict SLA or HA means for us. So I'll have my colleague Igor take over from here.
Hello, my name is Igor. So I joined MZ about almost 3 years ago. And when I joined MZ, we already had one game, it's Game of War, and that game generated a lot of traffic, as well as we had a lot of marketing traffic. And we need some tools to analyze this traffic. And by that time, data platform at MZ already built some data pipelines. The first version was Bash pipeline, with some OLAP storage to do analytics. But the problem with this pipeline was that it was, because by nature it's Bash pipeline, it was always delayed. And sometimes delay was up to 4 or even 6 hours, and it was for sure not acceptable for business. So as a solution to address this business problems, we built separate real-time pipeline, and we used different storage in memory database with completely different visualization tool. And it worked okay for a while. For example, 2 years ago, using this architecture, we launched our second game, Mobile Strike. But because it's two different pipelines, different visualization tools, it was very painful for our users. It was extremely painful for us engineers at Data Platform, because every time when business asked for, let's say, add new feature, add more dimensions, metrics to our data sources, we had to basically update two different projects, two different pipelines. So it was very inconvenient, very painful, a lot of, and I would say probably very expensive in terms of maintenance and operational cost. So as a solution, as Pushkar said, a year and a half ago, we started a new project and which was based on Druid. We chose Druid because Druid gives out-of-the-box Lambda architecture. So this is a very high-level overview how our current architecture looks like today. So we have Lambda architecture is basically you have real-time pipeline and batch pipeline, and for real-time pipeline we use Kafka, and then different streaming technologies such as Storm or Spark streaming, and data is getting ingested into Druid directly from Kafka. For batch pipeline, we dump data from Kafka to Hive storage, and then our batch pipeline reads this data, transforms right to HDFS, and later Druid index it. So even if it looks like two separate pipelines, in reality, it's actually the same. Both these pipelines, they share the same code base. It means that every time when we have to introduce some changes in our transformation logic, or we have to add more metrics, dimensions, we do it only in one project, and then we just deploy it to real-time and batch pipeline, and it's getting applied automatically. So it's nice if you have a lot of data, but this data is useless if you can't visualize, use it, right? If you can't visualize it, and to solve this problem, when we a year and a half ago, when we started to explore Druid, on top of Druid, by that time already, we found that already exists 3 or maybe even more open source visualization tools. And one of them was Superset. It's a project from Airbnb, and right now it's part of Apache Foundation. So a year ago we forked from open source version of Superset, and why we did it, because MZ business requires very custom features. So we forked from open source version and implemented a lot of our own like features, and also we fixed many different bugs from open source version. So nowadays, this forked superset probably one of the primary tool to do like all this data analysis, like do like slice and dices on top of data, you know, like, and it provides like different visualization, like charts, tables, pivot tables. So superset, it's not only one project on top of Druid which we use. For example, as Pushkar mentioned earlier, data science team uses Druid for data modeling. They pulls data from Druid and do some predictions, like such as like revenue predictions, some other calculations. We have like reporting from Druid. So, for example, every hour we send email to our executive team with data. So, because of that, Druid is kind of a very critical component at MZ. So, like, we have to provide exactly accurate data. And also, one of the probably interesting use cases how we use Druid is we use Druid to monitor Druid. So yeah, like we have like very small like Druid cluster which captures metrics from all our other production Druid clusters, and like we use it for data like performance analysis and monitoring. That's it for game analytics. I will give the microphone to Vikrant.
Thank you, Igor. Hello, everyone. Hey, my name is Vikrant, and today I'm going to talk about the marketing analytics platform at MZ. The marketing analytics platform is pretty much similar in terms of design of the game analytics that Igor talked about earlier. But in terms of marketing, we deal with many different data sources besides the game data. So if we go back and look at the previous slide where Igor talked about the architecture of the Druid and the pipeline, we follow the exact same design principle where we have a real-time job that's reading data from Kafka, and also a batch job which is reading data from Hive and doing the indexing and Druid. The only difference being that instead of just getting the data from the game, we also get some other data sources. So in the marketing platform, the different data sources that we have to deal with are the attribution service provided data. Like, for example, there are some click data. So whenever we show an ad and a user clicks on an ad, we get a postback which comes through an attribution service provider. Likewise, we also get some conversion data. So conversion data, you can think about like install events, purchase event, and so forth. Beside that, the other data source that we also get from external client or the external partners is the spend data. We run ad on a different ad network, which we talked about, like we have integration with 250 different ad partners. So we get all of this data through a different channel into our system. But now the question is, how do we make use of this data? Or how do we provide a meaningful information out of it? One thing that links all of this data is that they have some commonality in terms of the timestamp and some other fields. For example, the campaign ID or like product ID and so forth. One thing we could do is we can do a simple join across all this data set, but that is not going to work because of the volume of the data that we have. So this is where we use the feature of Druid. So basically the transformation process that we have transforms all of this data into and writes into SDFS. And on top of that, we call a Druid indexing process. The Druid indexer basically takes all of this data and runs an indexing job on top of it, which basically does a natural join across all of this data set. So when user is trying to make a query on this data set, it's going to return a natural join data between all these different data sets that we have. So since Druid is doing all the heavy lifting of the join part, that simplifies our framework where we process the data, because now the processes are now independent of each other, and there is and that reduces the complexity of all these applications that we have built. The other difference in the marketing world is that the data changes very frequently. For example, if I pull up a client data or the spend data, say for a particular partner today, and then if I pull the same data tomorrow for the same day, it's going to be different in some way. So now the question is, how do we make sure that our end report is consistent with the new data that we've got? So we've got to build some processes around it, the way we can detect that there has been a change in data for certain days, and then from there we can run indexing out. And this is where the architecture of Druid makes it really easy for us to do multiple backfills or do crunch the numbers again and again for historical data. So behind the scene, what Druid does is it writes all the data in segment. You can think about segment as a data store, which stores data for a particular interval. Interval could be a day, or interval could be in an hour. So those are all configurable during the ingestion time. So when we run the indexing tags on Druid, basically it creates a new version of this segment and then overrides that already exists in the system. And then it does a notification to the historical node saying that, hey, there's a new data available that is requested. So when user goes into UI and tries to fetch or does a query for the same time range, he's going to get the new data set out of the data. One of the very common use case of the marketing analytics system is the cohort analysis. This is something that marketers run on a daily basis. For those of you who don't know what cohort is, think about cohort as a way of analyzing data with some historical information in it. For example, let's say I got X amount of users today. I want to track how this user group is performing, say, on day 1 versus day 2 versus day 7. Using this data, the analysts, they can figure out how well a marketing campaign is running. So before, or in the SQL world, if we have to build a cohort, we have to process a lot of data. You have to process all the data from the beginning of the time, which is extremely expensive process, and also it's very time consuming as well. So, and also the side effect of this is that even though you have transformed your data, it's available in your storage, you can't still access that data until the whole cohort is built, which takes a lot of time. And again, this problem only grows bigger that when you have more and more data in your system. The way we have designed our transformation in Druid allows us to build this code at a query time. So basically, it eliminates all of the time that we have to spend in building this cohort queues and etc. So yeah, that's all from my side.
Yeah, so we are open now for any questions, or if you want to just move to the next presentation. Yes.
I think you mentioned that you have two separate clusters, right? You say you do two separate clusters, one for 1 year, the other one for a couple of months. I believe that on the Druid architecture, you can probably also configure the history data tier to multiple tier. Right. I think that also maybe is why you don't choose that way in your separate cluster. Right. Different time interval.
Yeah. So great question, right? So we did some experiment with tier setup. One thing is that it's a bit complex to operate. Also, when we are trying to see how the scales are coming in, we have to take care of like scaling whether one particular cluster or another. So definitely that's one of the other solutions that we can implement. And I think the straight answer there would be that it's a function of time. We have our focus at some other area of this infrastructure at the moment. And definitely with time, we will adopt to a more tier-based. I think we have a lot of other motivations too for adopting tier-based storage. In the beginning, when we started, one of the reasons why we did not do tier-based this thing is that all of these queries were running from same front-end tool, right? So basically, opportunity for you to supply the priority in the queries are very limited, right? And users, if you give that decision to the user, then the users always want highest priority, right? So that breaks the whole setup. But now with more application-driven architecture on top of Druid, we definitely have opportunity to reconsider that.
So you talked about the batch process where you had a HDFS layer. So is that like a multi-tenant HDFS that you're using both for deep storage for Druid and high processing, or is it two separate clusters?
So the Hadoop cluster that we use is a multi-tenant cluster, and Druid is so multi-tenancy could have basically multiple dimensions in which you can apply multi-tenancy, right? It could be in terms of applications, like different applications running there. It could also be to separate like businesses from each other. Like you don't want one business to step onto others' resources, right? So we use Hadoop in multi-tenancy for both of these purposes. But I think when it comes to verticals for the businesses, we have separate Hadoop cluster. We don't like run different verticals on the same Hadoop cluster. Inside Hadoop cluster, again, to implement application level multi-tenancy, and also category of applications that needs higher priority or more resources, we use the YARN resource.
So, but the deep storage is the same HDFS.
Correct.
Can you tell me more about your cluster, Druid cluster, like the nodes?
We don't talk about our infrastructure numbers like as at this point of time, but I can give you some of the examples which would help you understand how it is. I think we categorize our implementation of Druid infrastructure into three parts. One is basically coordinators which are running, and coordinators run on cheaper hardware. Then the second category of machines that we deploy is where our data runs, like both historical and the middle managers running the real times. For this part of the system, I mean, for our data nodes, we deploy pretty amazing hardware. Like we have Fusion IO running on each of these machines. Again, for broker, we deploy pretty cheap machines. So that's how it's organized. Anybody else? All right, we'll move to the next one. All yours. Thank you.
So just join audio and then you want okay. And then direct share screen. Okay, let me do. Okay, let's start this. And I think this is share screen. And do you want to go into full screen? This one. Okay. Sure. We just reset. Okay. That should be okay. Yeah. Is it on? Should be on. Yep. Okay.
Hi, everybody hear me? Okay. Thanks, MC, for hosting this meetup, and thanks all for coming. Am I audible? Thanks. Okay. My name is Anand. I work in data team Slack. I work mostly in the data infrastructure side, and my focus mostly on getting the real-time infrastructure. That includes some of our Kafka clusters and Samza and Druid stuff mostly. I'm going to talk about measuring Slack API performance using Druid. So just out of curiosity, like how many people are using Slack? Oh, so nice. Yeah. So as you know, probably Slack is a team communication platform. A brief history about Slack is like public launch in 2014, 800 plus employees across 7 countries worldwide, headquarters in San Francisco, and it's been used across diverse set of industries like software technology, retail media, you name it, and it's getting expanded. As you know, like Slack is kind of an interesting product. Like it's one of the rare enterprise product get adopted by word of mouth. Like people really used it, like really love it, and then shared. Mostly the growth is basically word of mouth. Right now we have around like 6 million daily active users, and each user is like spending more than 2 hours actively doing on Slack, and 55% of our users are like outside United States. That's kind of remarkable for a Silicon Valley startup. So agenda for this talk is like a bit of history, like basically set the context of like what is the growth looks like in terms of the data team, and then like some of the internal like tools that we use, and setting the context behind how we end up with like improving infrastructures and some of the use cases that we're trying to solve, and mostly what are the challenges that we face down the line, and like how we wanted to solve those things. So a bit of history. So March 2016, like as you know, Slack is like fairly new. March 2016 is where like the data engineering group being started. Before that, it was like all few folks from different teams, basically trying to do something on data. March 2016, where we formed a data group. At the time, it was like five data engineers team, like Slack employs like 350 plus, and active users at the moment is like 2 million. Just for like year and a half, we just 10 engineers so far in our data team. Slack employs like 800 plus, and active users are like more than 6 million per day. Data usage in Slack is like 1 in 3 in Slack actually using some way of interacting with the data infrastructure, either in real time or in a batch mode. We have around like 500 plus tables in batch systems that include the snapshots and derivative tables. We are getting fairly like 400K events per second at our peak load. So at Slack, it's all about slots. Slog is it's what the metric collection that we do. It's basically a contract between all the operational system or like any system that deployed in Slack and how they interact with the data warehouse system. Slog is nothing but a one giant script file that basically has what are the metrics that are actually collecting from different API calls or like any system that we use. The way it works is like, let's say an API call trying to log something. At the very first API call, the slog object initialized, and as the stack trace goes through, and they just add more and more events, more and more metrics to that, and when the API call finishes, they flush out the data back to Kafka. So it's very nice. Instead of having JSON-based approach, like it's having a very finite, visible contract between the metrics that we collect across different systems and the data warehouse system. So like kind of having a finite agreement. Well, not exactly. It's all about slog as we grow. There is clogs, flock, slog, like all sort of slogans getting added into that. Clog is basically the clients wanted to directly log certain things, like all the Mac client and the iOS clients trying to log directly to that. And we flattened all the slog strip data structures in the data warehouse system to make it easy for querying and all sort of things. So there are like, there are more slogans being added after that. It's very confusing. So one of my colleagues basically joked about this, like log means an egg in Tagalog. So it's like flog is like a fried egg, clog is a canned egg, and slice is like slog is kind of a sliced egg. So this talk we care about mostly sliced egg. So slog is our area of interest mostly. So at heart, data team is mostly collecting slogs, and we collect slogs and we denormalize it. We create more derived data and try to get inside of it. Most of the business metrics being driven by slogs. So how do the infrastructure's use case looks like? So what can go wrong if Slack API performance degradation or something like? So Slack fundamentally a productivity tool that's mostly used by the knowledge workers. So if any API degradation or any part of the application is not working, then you feel that your productivity is going down. So we wanted to be more proactive on that and try to understand what is a performance bottleneck and the fact that 55% of users are like outside of US. There are certain latency issues to be added into that. So we wanted to add more proactively to address those issues to give a good customer experience. So we want more of Slack Loves. So that's what we aim for. That's, we believe, gives more good customer experiences. So our number one goal in terms of looking for any real-time systems, or especially looking for Druid, is to get the performance monitoring. We deployed so many different components inside Slack, and we wanted to know how the experience of the users, the engineering and customer experience team should able to detect the performance bottleneck proactively. That's the number one goal. We don't want some users telling us like, okay, this is not working for you, this is not working for me, this feature is not working for me, I'm not able to log in. Things, instead of that, we should proactively like tell the customer team that this is something is happening and we are looking into that so that you can give a good customer experience out of it. So at a very high level, this is our real-time pipeline looks like. There are different other boxes already there, but this is kind of a very high level view. So web app is where the API is all there. And Bruce is kind of a nice sidecar kind of a project. It's a very nice tool that kind of installed across all the machines and collect slog and send to Kafka. And we use SAMSA to kind of slog, as you mentioned, it's like a one complex thrift structure, but in Druid, we wanted more of a flattened structure, and we don't want to like index everything. We want like more selective things, right? So we use SAMSA mostly for like transformations and like filtering and all sort of things. And then we write into Analytic Kafka, which is a new Kafka cluster for us. And we use both Tranquility and Druid, mostly a push-based ingestion into Druid. So Tranquility basically subscribe to Analytic Kafka topic and then ingesting into Druid case. Why a separate Analytic Kafka is like, as you can see, like the DW Kafka is like, slog is like one of the topic, but we are also kind of ingesting so many other topics. And this is a critical piece of the infrastructure for the rest of the data pipeline. So we wanted to keep the load like very predictable on DW Kafka. And besides, so that we introduce a new Kafka, because the nature of SAMSA, SAMSA and Tranquility kind of works always right back, and the load goes unpredictable. And the nature of Kafka is like, it's read from the same reader. So the write goes to the reader and the read comes from the reader. So the number of bytes in and bytes out always given a very unpredictable behavior on that. So we have beside that, like the newer Kafka clusters kind of very easy to understand, like upgrade and verify certain things. The reason is, as you can see, Analytic Kafka is fairly stateless. Like if you wanted to upgrade another Kafka cluster, you just need to spin off a new Kafka cluster and read out the SAMSA pipeline to a new Kafka cluster, and you can run the older one. So it's very easy for us to upgrade and test and be more robust in our infrastructure without worrying about disturbing the whole pipeline altogether. Right? And so we understand, like based on our experience, like smaller Kafka clusters are really more straightforward to operate than having a large giant Kafka cluster and always trying to partition, rebalancing, sort of things to run it manually. There are a few very interesting open source tools available to automate the partition rebalancing, but so far we are very comfortable with like operating many small Kafka clusters than like one giant Kafka clusters, right? So this is a performance monitoring pipeline looks like. The Samza process is like basically an abstract view of what is our Samza jobs look like. The slog router basically deserialize thrift back into a slog object. And then the FUF converter basically convert that and select whatever the selected metrics that we wanted to write. And the flow goes the same way. So we use few of the metrics calculation, like approx percentile, like Druid histogram extension being used for approx percentile. So it's very critical for us to understand what is our P95 and like how much variation that we have in the API side. So and the unique, like it's very important to understand like how many users are like impacted below P95 and like what is the performance variation across teams and which specific team is actually affected and all sort of things. And we have a nice Slack bot integrations along to that. So like if something goes wrong, there's a Slack bot integration basically published periodically to metrics to a channel where most of the interested party in that responsible for maintaining different services always watching, and then the information kind of push towards them to act based on that. That's our experience on like performance monitoring. So at a very high level, things should be okay. At a very high level, this is how we set up Druid cluster. All of Druid is in AWS, and we use S3 for deep storage, Zookeeper, and MySQL for all the metadata information storage. We use Tranquility, and Tranquility basically writing to middle manager. And the beauty of Druid in this case, like you can provide fault tolerance of each and every component. That gives us so much flexibility in terms of operational point of view. So you can see like we have set up an fault tolerance across different nodes. We deployed overload and a standby overload coordinator also, like we deployed like a couple of coordinators. The way we set up middle manager is very interesting is because we actually implemented an auto scaling features on middle manager. We are not using the inbuilt Druid auto scaling features because in order to spin up a new machines, we need to tag along a certain, there are some VPC groups to be attached. There is some EC2 instance to be tagged and properly labeled. So we use Chef and then Terraform for provisioning a new cluster. So it's very hard to put in those infrastructure into existing Druid EC2-based auto scaling. So the way we do is like we're running periodically a job that basically query overload and try to find how many tasks are running. And we have a maximum task that can run for each and every middle manager. So we can find the ratio, like how many tasks is running versus what is our limit. If it is, so we feed those metrics into Cloud Metrics. And if it is, the ratio is more than 80%, then we tell autoscale group to provisioning a new middle manager node. So that by if sudden load increase or some zombie task kind of hanging in there, we can save our middle manager for some time. The way we do auto, like we also do the scale down. So the way we do scale down is like if a node is not running any task for like 60 minutes or so, and we're running a periodic task that mark this node to be removed, like deprovision it. So we have a periodic like the infrastructure right there is a periodic cron job is running. Like if certain node been marked as ready for deprovisioning, it will take care of deprovisioning and all sort of things. So we just make it like if some task is like if some node is not running for the task for a certain period of time, we mark them ready for deprovisioning, and the cleanup job will take care of the rest of the things. We do the same thing for historical node. In the historical node, in our case, we monitor segment size. So we feed segment size back to Cloud Metrics and say, like, if it is exceeded, segment size is exceeded a certain threshold, we provision automatically a new historical node. The brokers are the same way. For the broker metrics, we feed all our CPU metrics and like what is the memory usage of each and every broker. And everything is like brokers being deployed behind Elastic Load Balancer. So load balancer trying to load balance it. And if certain threshold goes away for the brokers, it's also dynamically scale up and down based on that. So we provide all those auto scaling on the 3 critical part of Druid infrastructure for the middle manager, historical node, and broker node. So if something goes wrong, it gives us some more time to react rather than just to be always on alert for these things, which is one of the nice thing to be having in Druid. It's super critical for us because we are pushing forward for performance, and you actually make some decisions out of the infrastructure. It is super critical for this infrastructure to be stable for you to make any decisions out of it. Right? So yeah, that's how we do auto scaling things. This is just to summarize: middle manager auto scale based on the number of running tasks, and a historical node auto scale based on the segment size, fault tolerance deployed for overload and coordinator, and brokers auto scale, and then behind load balanced by ELB. Yeah, challenges. I think the number one is like cascading failures. I think this is the cascading failure actually pushes to adopt auto scaling on the middle manager. There are some cases like you got some, the handoff is the most critical part in Druid. So from the real-time ingestion to the batch, like to the coordinator node, if something goes wrong, the task is just hanging and so creating a zombie task. And then as it's started to pile up, it started to block the new ingestions. And it's not only going to block the particular pipeline, it's going to like kind of block everything because you don't have any open slot onto that. So that zombie task basically like pushed us to adopt this auto scaling features. It would be nice if you can like kind of resource allocate like a certain slot to be opened for certain pipeline, like tag along. But until then, like I think auto scale is kind of trying to prevent that issue. Forward index file, I think this is one of the most critical thing that we are constantly looking on that. Druid is very good when you have a finite number of dimensions you have and what metrics that you're going to measure it, right? And it's give you nice indexing and all sort of things. We are seeing some use cases like, okay, I wanted to see what is happening in the last 5 minutes and what things and the aggregated metrics. But if something goes wrong, I wanted to see the detailed view, like what actually went wrong. For instance, audit log. In this case, like security audit logs is like, we can always alert like last 1 minute what happened. And then the security wanted to have like, okay, I wanted to list out like what are the events happening those within this minute. And because some of the events and some of the fields can have like an increment key, like it's very high cardinality to index into it. And that's when we got into Struct, like we forced to adopt a new system to kind of, hey, you can see the aggregated metrics and alerting that, but if you wanted to go detailed view and you have to maintain that different, different system altogether. It would be nice if you have like kind of a forward index things, like you can exclude certain dimensions to be indexed, and then I should still able to query that things. So we don't need to maintain like 2 different kind of systems. This is one thing that we are looking at how we can solve this problem. Still a challenge. SQL, obviously, people love SQL. I think it's hands down, it's SQL wins. And it's nice to see like a lot of push behind Druid to adopt SQL as a first class citizen. We're still at 0.9.2, so we still looking the way to adopt SQL and other sort of things to that. Bridge a gap between batch and real-time tables. This is another issue, sort of not a very painful things right now. Basically, the moment people get used to like a performance table that delivered on the batch system, and now you have a real-time system that delivered on that. And the fact that we use a Frogs percentile calculation, it's different across 2 different querying systems, and you tend to get like a 2 different results altogether, and then people got confused. And since it's a real-time system, it's kind of a newer one. You approach, like, people mostly say, okay, this is wrong, and it's very hard to kind of provide, like, prove them, like, this is okay versus not okay thing. So how do we bridge the gap, not only from the delivery point of view, but the user trust point of view? It's also a real issue here. There was some questions about, like, earlier about, like, how do we, the tiered based segregations and all those things. One of the things that we are looking at, like, Presto is kind of our main query language, query tool for a batch system. And Druid has all those deep, like, all the historical data in the deep storage. We are trying to see, like, if we can query directly into S3 instead of directly query into deep storage, instead of, like, giving a load into Druid. I believe Presto started to support push down aggregation somewhat. So we can start adopting that one so that we can make Druid as a first-class citizen like ourselves, so, like, source of truth, and we can give more uniformity across access for our users. This is the one thing that we are actually looking on to make it sense. Yeah, I think that's it. Thank you.
Actually, 1 second.
It takes a second. It takes a few seconds.
Actually, we are running almost the identical architecture machine.
Okay.
AWS. And I think my question probably is a little bit on the slope field, but it's in the architecture.
Okay.
Regarding the sensor. And we find out that the sensor by default configuration actually require a lot of CPU, right, for to run the task.
Yeah.
But however, I mean, if you like, based on that configuration, the default configuration, we require large size of the EC2 to support the sensor.
Yes.
But that the CPU we are using is almost
very
low, right? So I don't know whether you see a similar situation in your architecture.
Yes. So actually, we kind of over provisioned in our cluster. In our case, like, we use some R3 8X, but we actually see some, like, it's not like fully utilized. We keep it for a reason because we keep it for a reason because we wanted to have more reaction time to our system. Like, if some load goes out and off, so most of the things are like performance metrics. So when things go bad, people it's just going to have more load comes in. So even though the cluster is underutilized, it gives us like nice time for our folks to react, so that we don't need to lose the data in a critical time. So for holding up well, good for us. Yeah.
Can you talk about your architecture regarding to the data retention? Maintain the index because the index can how do you make sure that the size?
Yeah. So the whole infrastructure is hardly like 3 months old. Like, we are in production like a month now. So we don't really do any batch indexing right now. Our retention period is 1 week for each and every table, whatever we use. And the fallback for us, like, our batch system will be ready like within 4 hours. So the fallback right now is a batch system to query if something goes wrong. That's something that we are actively working on, that to add this backfilling and increase this retention period of it. Yeah. Right now it's like 7 days.
You have you on AWS, right? So you have I guess the product is used all around the world. So you have mostly in the US or is it all around? So basically, I'm trying to understand, you're running AWS. Do you have a single Druid cluster, or do you have different Druid clusters with different geographies?
No, we have only one Druid cluster as of now, one production, and that's hosted on US East. It's not like a multi-tenant or like multi-data center deployment so far. So that's something.
All your metrics obviously properly protected.
Right. Yeah.
So I'm wondering how you select Sensor versus Kafka streaming or Spark streaming?
Good question. So when we started streaming structures, like Kafka Stream is not there at the time, and Spark streaming was kind of not so stable at the time. Not sure how good it is right now. Samza is kind of very nice.
I'm talking about 4 months ago.
Oh, the Druid infrastructure is like 4 times ago. Like we have Samza deployment long before that.
Okay. Yeah. So this streaming is.
Yeah.
I'm so curious because you say Druid is very critical stability. How do you do monitoring?
Okay. Yeah, so we emit all the metrics into our metric systems, like that been maintained separately by the ops folks. I think we are using right now Graphite, but we are moving to Prometheus like this quarter. So yeah, we don't feed that into Druid. Like we don't do that. Right. Thank you.
Screen. Yep. Keynote.
And then maybe full screen.
Do you want to check the meeting? Is it working all right? Hey everybody, me again. In case you forgot who I am, or if you just showed up halfway through the talks, I'm Gian Merlino. I'm a committer on the Druid project, also a PMC member, and I'm a co-founder at Imply, which is a company that is built around Druid and which Pushkar talked a little about in his talk. As he mentioned, we provide a variety of products and services around Druid. So UI and management stuff, support. Also, we're hiring if anybody's interested in Druid jobs. But this isn't about Imply, this is about Druid. And so I want to move on to talking about the Druid roadmap. So I'm going to first talk about the very soon upcoming Druid 11 release. Release is imminent, and its release vote is actually already passed. It passed this morning, and so we're going to do release as soon as possible, basically. You should expect it later this week. I'm going to go through the headline features for this release. So there's a lot in this release. There's TLS, security. There's a security framework as well. So 2 security releases or 2 security features are headlining things. There's a float 64-bit column type we're adding. There's a cache and cost segment balancer for big clusters. And we've also made performance improvements to group by, which if you've been following the Druid releases, pretty much every release since for the past couple of years, I've included group by performance releases or performance improvements. And we made improvements to Druid SQL, which was new, I think, earlier this year. And it's also been improving every release. So the first thing, TLS, transport layer security, encryption of data in transit. This is a big one. So this combined with that other feature are really providing a security layer for Druid. So this encrypts data both from you to Druid and also internal traffic in the Druid cluster. What it doesn't encrypt is traffic between Druid and Zookeeper. And so for that traffic, you'll still want to have some sort of network firewall protecting it. But none of your actual data is in Zookeeper, just metadata. And as we've heard from the NSA, metadata is totally chill, nothing wrong with that. Your actual data is going to go over an encrypted line. The next thing, the authorization and authentication framework. So authentication, who are you? Authorization, what can you do? Both of those are part of this framework. This builds on some earlier work. We've had an experimental authorization and authentication framework in Druid for a few releases now, but there's some big differences. One is that this is no longer experimental. Another one is that the second last bullet point, it's always on. So the experimental one was you enabled it with a config property. Most people didn't enable it. It wasn't documented. It was more for sort of testing amongst the Druid community. But this one is always on. It's integrated with both HTTP and JDBC, the two APIs that we support in Druid. You can chain authenticators and authorizers, so you can have multiple kinds of authenticators, multiple kinds of authorizers for your Druid cluster. Maybe you want to support both Kerberos and LDAP, for example. And like I said before, it's always on. The default configuration out of the box we ship with is just allow everything, but you can change that, of course. And one cool thing I want to talk about is this is a little bit of a technical detail, but I think it's cool, so I put it up there. One thing we did when going from the experimental framework to the non-experimental framework is we added these authorization gates. And this is a cool thing because Druid has over 130 APIs. And one challenge in securing a system that has that big of a surface area that didn't used to have security framework and now does is that you want to have some sort of assurance that you actually implemented security in all the places that need it. And so our strategy there was to have an authorization gate where we actually have a process in the Druid, or it's a filter in the Druid server stack that is making sure that for every request, no matter what endpoint you hit, there is an authorization check performed. And if an authorization check is not performed, the request fails and an alert gets thrown out. If you see one of those alerts, file a bug. That should never happen. But that's the purpose of that gate is to identify these issues where an endpoint is not properly secured and block it before any data gets returned to the user. And so that's shipping as part of this as well. That also affects endpoints that are added in extensions, which is another really important reason for us to add authorization gates, because Druid does support extensions, and extensions can add new APIs. And so if you have an extension adding an API, these authorization gates will make sure that that extension API is not a backdoor if you've enabled security on your cluster. Next thing, 64-bit float columns. So this is something that was commonly requested, implemented now. So if you have data that's decimal, floating point, and 32 bits is not enough precision for that. So as you may know, 32 bits gives you about 6 or 7 decimal places of precision. 64-bit gives you somewhere in the teens, I think. So it's a lot more precision available from 64-bit storage. There's a migration path in the release notes. So if you want to use this feature, check the release notes and that'll show you how to use it. It's disabled by default in this release just for migration reasons to make it easier to migrate, but you opt in and the next release after this, it's going to be enabled by default. Another thing new in this 11 release is the caching cost segment balancer. This is a new segment balancing algorithm. So, one of the jobs of the Druid cluster is to balance data in the cluster. So as you might know, any distributed system that has data in it, HDFS, Kafka, Druid, has to have some kind of way to balance data in the system. Kafka is manual, so if you add a Kafka broker or Ruby broker, you have to manually shift partitions around. HDFS does it automatically, the name node does it. In Druid, it's also automatic. The Druid coordinator does it. And there's pluggable algorithms for how that's done. The default algorithm is the cost-based algorithm. We've added an ability to have caching for that. So the caching of the cost of the segments. And that helps a ton for clusters that have large numbers of segments. And so we've seen in benchmarks up to 10,000x performance boost in the amount of time it takes to balance data in a cluster that has a lot of segments. So down from a few minutes potentially to compute the optimal distribution of segments down to less than a second. Performance improvements don't stop there though. It's not just at balancing, it's also at query time. So like I said, we are always improving group by performance. The two big things we are improving in this release are we're multi-threading the slice sort for eating aggregation. So when we do an aggregation in Druid on the group by, let's say you have 6 CPUs, you're going to have 6 aggregation slices. Each CPU is going to work on one of the slices, and then they're merged together into a final result. In the previous version or the current version, that final merge is single-threaded, and now it'll be multi-threaded. So we measured that as a 10-20% performance boost, depending on the query. Obviously, it'll be more of a boost if your result set is big, and less of a boost if your result set is small, because it's parallelizing the merge that result set. Another big one is array-based aggregation. So if you're grouping on the string column, instead of using a hash table, we can use an array if the cardinality is small enough such that, because all the Druid string columns are dictionary indexed. So if the cardinality is small enough that we can fit every ID into an array, we use array instead of a hash table, save up to 40% of our time. Also SQL improvements. So like we're always improving group by performance, we're also always improving the SQL language, the SQL dialect in Druid SQL. Our first improvement earlier this year was to make it exist, and now we're mostly adding new functions to it. So we're adding a bunch of new functions. We're adding an explain feature that is better than the old one. The old explain feature gave you it basically dumps some internal data from the planner. The new explain feature actually gives you the SQL query explained as a Druid query. So you can then take that, copy and paste it, issue it as a native query. You can use Druid SQL to understand more about how Druid native queries work, and you can actually get better insight into what Druid SQL is doing when you run SQL query. So those are the big things in 0.11. Let's just hit that list again. So we have transport layer security. We have that security authorization authentication framework, 64-bit floats, improvements for clusters with tons of segments, improvements for group by, and then new functions and a better explainer for Druid SQL. And the last thing I want to talk about is beyond. So what are we thinking about doing after Druid 0.11? What's there for Druid 0.11.1, 0.11.2, 0.12, that kind of stuff, and eventually 1.0, maybe, probably, I assume, at some point. So this stuff is all stuff that largely people are actually already working on. There's the roadmap of ideas that we have that might be cool is a lot longer, but these are things that people are actually working on. The first one is Kafka indexing robustness. So the Kafka indexing service was something we introduced, I think, middle of last year or so. It's a exactly once transactional ingest from Kafka into Druid. It was meant to make it possible to do real-time ingest into Druid in a way that you don't need to have a fallback to a batch system for correctness. You can be assured that you're getting it exactly as it was from your real-time stream in Kafka. It works very well with the recently introduced exactly once transform feature in Kafka and Kafka streams. So with that feature plus Druid Kafka indexing, you can have a exactly once pipeline from data generation all the way to your analytics system, even going through stream processing. So that's a super powerful thing. And so we're working on robustness for that. So what I mean by that is we're trying to work out all the edge cases and corner cases such that when you set up a pipeline, it should work out of the box. Right now, it does require some tuning. And our goal is for the only one tuning parameter you should need to specify is essentially how much you want to scale out the ingestion on the short side. So do you want to use 1, 2, 3, 4 processes? Right now, it requires a bit more tuning than that. Automatic compaction is another big one. So this is something that a lot of other databases do, but Druid doesn't do. And so, just compaction is just when you write data to the database, you write data into a segment, and you write more data, it goes into another segment, you write more data, it goes into another segment. After a bunch of times of doing this, if your data is coming in at regular patterns or what have you, then you might have a segment distribution that's suboptimal. And so we want to do a compaction in order to essentially reshuffle, repartition your data to be optimally distributed. And so this is really something that's going to help with query performance. You can do this manually, and actually a lot of production Druid clusters out there do manual reindexing or manual compaction, essentially every night going and running a job in the Druid cluster that compacts all the data from the previous day. So a lot of people are doing it manually, and we're building a feature to do it automatically. Reducing reliance on Zookeeper is something else that we're working on. This is part of a larger project to make Druid more resilient and robust. So what we found is that a lot of the issues that people have when they're running clusters at scale happen when Zookeeper goes down. And when Zookeeper goes down, the Druid cluster goes haywire. So we spent a lot of time, so our strategy for the first few years of Druid was, let's try to get rid of all those issues. Let's try to make working with Zookeeper good. Let's try to make it so when Zookeeper goes offline and comes online, things recover properly. That project has not worked as well as we hoped, and so now we're embarking on a different project, which is let's just stop using Zookeeper so much. And so that's well underway, and there's actually, if you go poking around the code base, you'll see that some of it's already there. Not all of it's documented because it's still in that sort of experimental state, but if you're interested in testing it out or helping out, then check out the Druid development mailing list, where we're actually about halfway through this project already. A fourth one, boosting expression performance. So one thing we did to make Druid SQL so powerful, so Druid SQL supports statements like case, it supports complex conditionals, it supports complex arrangements of expressions. And if you're familiar with the Druid native query language, you know that for a long time, Druid has pretty rigid in how you can make queries. So you can only group by functions of one column at a time. You can't do functions of 2 columns. When you are grouping by something, it has to be grouped by a string, not by a number. So what we did was we loosened a lot of that up by building an expression system into Druid. And so the first thing we did was make it possible to loosen that up by building these expressions. And the next thing we're doing is making it fast. So right now, if you in Druid SQL do something that can be planned without expressions, it won't use them. And if you do a query that requires expressions, like having a case statement or a multi-column expression, it will use expressions. They do impose a performance penalty. The stuff we're working on, we're aiming to make them as fast as something written in native Java extension. So that's another project that we're working on right now. So if any of you use JavaScript functionality, JavaScript aggregators, JavaScript filters, the expression system now is about the same speed as writing something in JavaScript. They're about on par with each other. It does have better memory usage characteristics than JavaScript, which is nice. But performance-wise, they're about the same, and we're aiming to do better than that. Next one, improving SQL planning, simplification. One thing we found is that Druid SQL works really well for manually written queries, but it does not work as well at this time for queries that are generated by UIs and by programmatic means. And the reason is because programmatically generated SQL queries tend to be really weird, for lack of a better word. They tend to have a lot of useless operations, useless casts, useless arithmetic, and that's just because of the way the tools generate the queries. And so we're working on getting Druid SQL better at identifying when the things you're asking for are useless and cutting them out. And that's a performance thing. Broker resource management, so that's just about making it so we can better coexist multiple users on the same cluster. And then ability to disable or customize indexes. This is something related to what the previous speaker was talking about. You want to have the ability to have a column that doesn't have an index. You want to have the ability to have a column that has an index. It's maybe not a bitmap index. So that's something that we've loosened up the internal framework that Druid uses to think about indexes, and then at this point, it's mostly a matter of actually implementing other kinds of indexes and implementing a switch to turn off the bitmap indexes. So that'll be something coming up soon. And that was my last slide. Any questions? What's up?
After indexing, what's the Cyber is taking care of nested JSONs?
So the question was nested JSONs. It doesn't fall under that, but we actually are taking, well, it doesn't mean by taking care of it. We're doing something about it. What we're doing about it is, so there's already something called a flatten spec, and that's something that already exists. You can flatten data out. We're adding a transform spec. I don't remember if it's in 011 or if it's going to be the next version after 011. I think it's the next version after. But a transform spec works with the flatten spec. So you can flatten things and you can transform them in various ways. And so between flattening and transforming, you should be able to do whatever you need to get your nested JSON into Druid's data model. Druid's data model still remains basically a flat data model. So if you need to have something so nested objects are fine. What tends to be a little bit tougher to model is if you have an array of objects. So an object with an array, and inside that is more objects. For that, you tend to usually want to do something with multi-value dimensions or flattening, and then it becomes use case specific. But as far as the tools that you have. You'll have flatten spec and transform spec, which enables you to do a lot more without having a pre-processing step. Yep.
Do you have stats on the CPU for waitlist and using waitlist authorized?
So the question is, do we have stats for the performance impact of TLS? So we didn't test it in the way that you would want to test it to get the worst number. So we didn't test the worst. The worst case is if you're transferring like a lot of data relative to your results. We tested it in normal cases. So just running a normal cluster with an actual real workload. So one of our real clusters before and after upgrading to TLS, and we didn't notice a difference in CPU use. So we didn't measure necessarily the absolute worst case you could think of, but in what I would say in typical cases, it didn't really add any overhead that we could measure, which does make sense because most of the work Druid's doing is in the actual processing and aggregating of your data. Like it's not like a static web server that's basically doing nothing other than throwing bytes over the network. It's doing a lot of other work. And so the TLS cost gets kind of lost in the noise. Yep.
So one pattern that we do is like most of the queries goes to the cost freshness of the data that we into that, and we have a simplification factor of starting free. So what we do is that all the queries goes to the same node, and we'll start getting like all these users want to query all these numbers. Is that any way that I can do like status across starting?
Sorry, I don't know if I totally understand what you're asking. Are you asking is the problem you're saying that your data is distributed in such a way that the latest day, which is what people most want to query, is not distributed across every node, and so some nodes are kind of hot? Yeah. Okay. So I guess I have two answers to that. One is that if you have enough segments in the most recent day, such that that number of segments is equal to or larger than the number of nodes, even better if it's a lot larger than the number of nodes, then our default cost-based data balancer should balance that out for you. That's what it's really designed to do is the cost it refers to is it has a cost based on if two segments are in the same interval, it penalizes having those two segments on the same data node. And so what that tends to do is spread out segments that are from the same interval on different data nodes. The time where that doesn't work well is it doesn't work well if the number of segments for the most recent day or two is a lot smaller than the number of data nodes you have. And that in that case, it's not really possible to spread them out well. So there's a few things you can do in that. If you are in that case, there's a few things you can do. One is you can increase your replication factor such that, let's say you have one segment. Let's say in the extreme case, it's like one day you have one segment, and that one segment gets 90% of your queries. So you can increase your replication factor for the most recent day to be, let's say 8, if you have 8 nodes. And so you can have different replication factors for different time ranges. So you can say most recent day, high replication, other days, low replication, and replicate the most recent day in more places. You can solve it that way. If you're not in that case, if you are in the case where you do have a lot more segments than historical nodes, Druid should be doing that for you already. And if it's not, then come talk to us. Yeah. Yeah, so the question is, we talk more about broker resource management and I guess also about what's going on in historicals. So the reason historicals are up here is because historical resource management actually works reasonably well already. So historicals actually have relative to brokers, they have a pretty sophisticated resource management schema. Actually, when you set a priority on the Druid query, that actually only affects historical behavior. It doesn't affect broker behavior at all. So the brokers are not aware of what a priority is. They just send queries to historicals. The historicals interpret the priority, and then they allocate their CPU resources accordingly. The historicals also have a pretty good separation of memory and disk use per query, such that queries aren't grabbing all the memory or all the disk, and you can have multiple concurrent running without them grabbing each other's resources. So historical generally doesn't have too many resource management issues right now. The ones that we see in production clusters tend to be on the broker level. And that's because, again, the brokers are not aware of priorities. It's a lot easier for one query on the broker to grab an excessive amount of memory, that kind of thing. it's possible for the broker to get sort of blocked up with too many low priority queries and not be able to handle high priority ones. And so most of what we're working on with broker resource management is having it have the same kind of thing that historical does, where you may have, have it actually respect priorities, have it have something like swim lanes where queries don't get out of their lanes, and generally make it so it's a little less Wild West inside the broker and a little more strictly managed. Just so you know, for people that do have broker issues today, due to the relatively, I'll call it, simpler resource management strategy of the broker, people that do have issues with that today, most people today are solving it by having different pools of brokers and using different pools of brokers for different apps. And they may all go to the same set of historicals, but the broker pools are different. Yeah. You say GPUs? So nothing that is good enough to make it on this roadmap slide. Someone did some experiments with GPU processing a couple of years back for, I think, one of the aggregators. Didn't get very far, found something interesting. Yeah, so, yeah, no one's working on it right now, as far as I know. Yeah. What's up? Speculative execution, are we planning to do that? That's a good question. We generally are not planning on doing it. So we're not planning on doing it. I can tell you why we haven't done it yet, and we'll see if that reasoning changes in the future. So the reason we haven't done it yet is because for a large part, Druid targets queries that finish quickly. So we're trying to build systems to back APIs that want fast responses and to back UIs where people want to have interactive usage of it. We generally target queries that finish quickly. And for queries that finish quickly, speculative execution is less, it's less valuable because the odds of a machine dying mid-query is a lot lower. I mean, when a typical query takes, so for MapReduce, typical MapReduce job, if it takes 20 minutes, the odds of a machine dying somewhere in the middle of it is pretty high relative to a Druid query where you expect it to take more like a second or two. So that's why we haven't done it yet. To the degree to which the Druid community starts getting more interested in longer running queries is going to affect whether that matters or not. But at least right now, the Druid community is largely not that interested in longer running queries. So, yeah, so the question is, what's the vision for indexes? So the first one to implement is none, which is easy. It's actually a lot harder than you might think because there was a lot of assumptions in Druid that every column is indexed, and those have at this point all been wiped away. So implementing no index is a lot. Now it's actually easy. It didn't used to be, but now it would be. As far as actual other indexes, so there's a thread on the dev list a few months back that was about implementing numeric range indexes. That seemed interesting to me. So you have a numeric column, you want to do range indexes on it. That seems cool. There's actually already spatial indexes in Druid. I think we've talked about them a bit. They are, if you looked at the Druid code base and see how they're implemented, they're totally specially cased everywhere. So the first project there would be to take that special casingness and make it not a special case. They were implemented in a time back when there was no real framework for adding things to columns, and they're kind of like a hack. But bringing them into the new world is cool. Yeah, I don't know. Probably string range indexes too. I mean, we have string bitmap indexes, but a string range index, like a tree index, would be cool. But the ones that at least I would have my sights set on first are making spatial part of that index framework and not a special case, and a numeric range index. Because right now we don't have any columns, or we don't have any indexes right now that are suitable for numeric columns. Any other questions? What's up?
Is there any need to do you support zero cross,
So the question is, do we support Azure Blob Storage? I think there's an extension in the code base that says Azure Blob Storage. You're nodding your head yes, I believe you. You look trustworthy. Yes. I'm willing to say yes on the strength of this man's head nodding. Does anyone recall if it's in core or contrib? So in Druid, we have two kinds of extensions, core and contrib. The core extensions are supported by the Druid, I guess the Druid committer group, and so there's an issue with that. It's treated as just part of Druid as anything else. The contrib extensions are part of the Druid code base, but they're community contributed, and they're kind of supported by whoever contributed them. And I don't remember which one it is. I don't remember. I would say, so I'll answer that from the perspective of Imply, my company, which I can talk about a lot more affirmatively than I can as for Druid. So at Imply, our general stance is we'll support them if we have a customer that needs it. And generally part of that will be pushing it to become a core extension of the Druid community. At least for me personally, that's the main thing that would cause me to push something to be in core. Imply doesn't drive all of Druid development. We drive a lot of it, but we don't drive all of it. So, someone else might push to get it in core. It might already be in core, I just don't remember. But it's community driven. So whether the community drivenness is coming from us or coming from someone else, it's community driven. So if it's not in core and you want it to be, then just start talking about it and it'll probably end up there at some point. That was a rambling answer. Anyone else? All right, thanks everybody.
All right, I really appreciate all of you coming here, and I thanks Imply team for allowing us.